Welcome back, everybody. So I'm assuming if you're here, you've already watched the previous video where we sort of define the differences between an empirical and a molecular formula. That was pretty easy, pretty straightforward. I won't rehash that. So if you haven't, you may want to go back, look at that one on empirical and molecular formula basics. Watch that first so you have a bit of understanding of the definition of these two terms, so that as we're going over this, it'll make sense why we're doing what we're doing and why we get what we get, the answers that we get. So here's two examples. I'll try to go through this as quickly as possible, but at the same time not overlook the details for you. So first question, so we've got quantitative analysis of a substance. Basically it tells us the percentages we've got of sulfur, sodium, and oxygen. So we basically want to find out if by looking at those percentages, that's given us some information about ratios, because a percentage is a ratio, right? So to get a percentage, you remember your basic math. To get a percentage, you would have to have had a decimal. If you had a decimal, it means you had a fraction. So you had some portion of something. So if you think about it, anytime you write a compound formula for anything in chemistry, the formula is telling you the ratio of atoms in that substance, right? So, and that ratio never changes. So if that's true, then it doesn't matter how large your sample size is. You could have a sample size, this big, or you could have a sample size this big. It doesn't matter. That same ratio, it occurs at every level, from just one molecule of that substance to an Avogadro's number of those molecules, right? 1 mole of that substance. So here we've got a certain percentage. So you don't know how much substance. If you read this problem, nowhere does it say you have so many grams of this, so many grams of that. Start with so many grams of this, and here's what you've got. So you ask yourself, how am I going to do this if I don't know exactly how much I've got? How much is on the scale? So understanding the concept of ratios, we realize the easiest thing is to use this concept that when we're talking about percentages, you have 100% of whatever the sample is that you've got, right? So if you think about it, I don't care if you have 2 grams, 200 grams, right? That 2 grams or 200 grams represents 100% of the sample. So no matter what, your ratio of atoms stays the same. That means the percentage of those atoms stays the same. So whenever you have a problem where information is given to you in this fashion, then what you do is you assume a sample size that equals 100%. So if it equals 100%, that means you could assume a 100-gram sample. All right. If 100% of if you have a 100-gram sample and you had every single gram there, you'd have 100% of the mass, right? So mathematically, this makes sense. So now we can go back to this right here, and we see what we've got. We see something that says that 22.65. Let me put that in a different color for you. So we've got this much sulfur, we have this much sodium, and we have this much oxygen. So understanding what we've just talked about, we can go, wait a minute. So there must be 22.65 grams of sulfur, right? And that means that there must also be, let me give some space here, there must be 32.38 grams of, what is that, sodium? Yes, sodium. And then there must be 44.99% oxygen, right? So if you add those numbers up, let's see what we get here. Let's see, 22.65 plus 32.38 plus 44.99. You should get 100.02, and so that's perfectly fine. If you think about it, you've already learned from your basic math and chemistry that there's always like a standard deviation. There's always a little bit of error. You could have plus or minus a certain amount. So whenever we're looking at stuff like this, you're always going to have a little bit more, a little bit less, but on average, it comes out based on the error in your tool to be that, right? So we basically have 100%. So now the question is this. So we have to go back and we have to remember that when you look at a compound formula, um, the subscripts, the numbers that are in the formula, tell you something about molar ratios, right? So if you're looking at one molecule of water, then you've got 2 hydrogen atoms and 1 oxygen atom. That's easy. If you had a mole of water, 1 mole of water, Avogadro's number of water molecules, then you essentially would have 2 moles of hydrogen and 1 mole of oxygen in that 1 mole of substance that we call water, right? So we have grams here. We have a mass unit. You have never seen a formula where you have 22 sulfurs and 32 nitrogens and 44 oxygens in it. I mean, you're just not going to see that. Now, you might see something with that many oxygens in some incredibly large macromolecule in some really sophisticated organic chemistry class, but that's not this, not even close, right? So what we have to do is we look at that and we go mass. Mass isn't going to help us, but moles would help us a lot. So we need to convert grams into moles. So we just simply use basic molar mass. So we use our basic dimensional analysis, and how many grams of sulfur are there in 1 mole of sulfur? Well, go to your periodic table, right? And so remember, right there, right? Oops, sorry about that. So remember right there, we've got, it says 32.066. So in previous videos and in class, I've told you that based on our the tools that we have in class, the estimated digits in the hundredths place. So we're going to take this and we're going to go to 32.07, right? So let's go back here to our problem. So that means we've got 32.07 grams. Let me make that a little bit better for you. All right, and that looks like 9 with an S. Let me rewrite this. I want to make sure that there's no confusion for you. Grams of sulfur. All right, now you should see grams of sulfur goes away. All right, so let's do some math here. We've got 22.65 essentially divided by 32.07. That gives us 0.706267. Okay, and then the only unit that's not canceled out is moles of sulfur. Now, you've never seen a formula where we write 0.7 in a formula. You don't write H 2.40.9, right? We don't do that for water. We just say H2O and the one's understood, right? So we're going to have to do something with that number, but we're going to get there. Let's just do this. Let's go through this with everything right here, right? So let's do this. Let's just follow this process for all of these right here. So we need in 1 mole of sodium. What do we got? So let's go back to our periodic table. And remember over here, sodium 22.990. We're going to use 22.99. All right. So we come back over here. And we've got 22.99 grams of sodium, right? And so you should see that grams of sodium cancels out. And so we'll come over here. We got 32.38 divided by 22.99. Double check my math. You should see 1.408, right? 1.40843, right? So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 3. We'll go with an 8 right here. Why not? And then, of course, that's moles of sodium. So I say why not because you just need some extra numbers. We'll figure out in a second how many numbers we want to use, but just put some extra numbers for right now, okay? How you doing? Coffee break. Love that coffee. Well, obviously we know what to do with this right here. All right. So, all right, here I wrote percentage. Those of you who were watching this earlier probably realized, oh, he'll go back and change that to grams when he gets there. Here we go. All right, so go back to oxygen. Oxygen 15.999, 16.000, right? So we've got 16.00. Oops, oh, that does not look pretty. Well, let's try this again. One more time. 16.0, we're going with that one. Grams of oxygen per 1 mole of oxygen, right? And so now, cancel that out, that unit canceled out. Let's do some math. We've got 44.99 divided by 16. You should get 2.811 and a bunch of numbers, right? So we've got 2.811875, and of course that is moles of oxygen. All right, so we've got some decimal numbers, which means we've got fractions, right? Well, you've never seen a formula again written with fractions, right? If you have a decimal, that means you basically have an improper fraction, right? So you have that many something. So 1 and something else, right? 2 and something else. We got improper fractions. So now let's think about this. Here's sodium, sulfur, and oxygen. So in a previous video and in class, we've talked about that empirical formulas. Two things, right? Two things. One is it's the simplest ratio, and two, we tend to use those for ionic compounds. So you should recognize that right here, this is going to form an ionic compound, and always what's first in the ionic compound is the metal. So if you think about it, we're going to have this. We're going to have sodium, and I'm going to put an X because there's going to be some integer here. And then you should see that sulfur will probably come next. There's an X. And then O next. We don't know what it is. Now, once you do this stuff enough, you can look at it and you can make an educated guess. Right now, we need to figure out what those numbers are. So here's how you do this. We've got this in this order. So right now, according to this problem, we've got sodium, and that is 1.4084. Now, I'm going to go 4 digits after the decimal for 2 reasons. One, we see 4 sig figs on this problem. Now, I know that's 5 right there, but very often you will see that these problems, you tend to go 4 numbers after the decimal place. And the reason for that is this knowledge right here, this information. So you'll see how on the periodic table that we use in class that there's 3 numbers after the decimal place. Precision and accuracy in labs occur because we basically use equipment that goes out way after the decimal. I mean, multiple places, right? So to get a more precise calculation, to be more accurate, and so that we have precision in our measurement, we go several decimal places out. So as a rule of thumb, I'm going to want you to go 4 decimal places when we do these problems here. Sorry about that. I swiped in. I'm not changing this video as a result of that. You saw what the weather and the time is now. Good job. So there's sodium. Next we've got sulfur. Sulfur, we see it's 0.7062, right? Then we've got oxygen, and that is 2.8118. Now notice I'm not rounding up any of my numbers. Remember, you round one time and that's at the very end. All right, so you look at this and go, well, that doesn't look like anything we've ever done. So what are we going to do here? Well, let's think about this. If we were to divide each of these by the smallest value that's there, we could reduce it. We would reduce the smallest one to a ratio of 1, right? So let's think about it. The smallest number here is this number here. So if we divide everything by 0.7062, if you think about it, 0.7062 divided by 0.0762, that is 1. Now, 1.4084 divided by this number, I'm going to put it in the calculator for you, but you should be able to see that this is essentially, essentially this is 14 divided by 7. We should get something like 2, right? So 1.4084 divided by 0.7062, and we get 1.9943 and a whole bunch of other numbers, right? So let me come back up here. We see that right here, when we divide this out here, we get 1.99, right? And then you should be able to see here that if we were to highlight this, that this is essentially 28 divided by 7. That's 4. So let's see what happens. We've got 2.8118 divided by 0.7062. And we get 3.981 blah, 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 right? So far, this is working out. This is working out nicely. So what do we got here? 3.98, right? So after we've done our math, what we have is sodium 1.99, sulfur, which is 1.00. We have oxygen, which is 3.98. Well, again, we have to use integer values, right? So 1.99, that's 2. 1.00, that's 1. Ones are understood, don't write them. 3.98, that's 4. Now we've got something that looks extremely familiar. There's our formula. There is our empirical formula. This is our empirical formula. And so this other thing here says for us to name the compound, we just go back to our basic chemistry, and we know that we've got sodium sulfate. That was pretty easy. All right, so let's recap that. We took the percentage, we turned those percentages into the mass, assuming we had a 100-gram sample. Always assume you have a 100-gram sample unless you're working with a problem where you know the exact amount of the sample, and then you're just working with that. Right? That's still your 100%. It's just the math would just be set up a little bit differently, but still essentially the same thing. Got moles, and then we're taking those moles and realizing how can we reduce that to an integer value. That's basically what we had to do, right? That's basically what we had to do right here, was reduce that to an integer value. Okay, so there's your empirical formula. All right, now let's do this problem down here. Let's do this problem down here. All right, let me bring this up here. Empirical formula of phosphorus and oxygen, right? So you've got a pair of phosphorus and oxygen. I'm going to put in the X's because according to this, that's what it is. It's telling us that we've got some ratio of atoms of phosphorus and oxygen. So Px, OX. X just means some integer, right? We don't know what it is. Tells us that we've got 2 parts. We've got 2 parts phosphorus and we've got 5 parts oxygen. Experimentation shows that the molar mass of this compound is 283.89 grams. So let's think about this for a second. We're told we've got the molar mass of this. So let me write this down over here. So molar mass is 283.89 grams per mole. Okay, well, let's find out if this ratio right here, if that's true or not. So phosphorus, if we look at phosphorus, there's 2 of those. Well, I'm looking at my periodic table, but let me bring this up here for you. All right, phosphorus 30.97. All right, so let's go with 30.97, right? So here we've got 2 phosphorus times 30.97 plus the oxygen, and we've got 5 of those. Remember, that's 16.00, right? Make that a little clearer for you, right? So let's do this here. We've got 2 times 97 equals this, plus we've got 5 times the 16. You should get 141.94, right? 141.94. Now, we look at that and we realize, okay, if we're talking about X amount of something, that we would be talking so many grams per mole, right? Because we're talking about a molar substance. We're talking about a certain ratio. We got something on a scale, so we've got a certain mass of this stuff, right? All right, so let's think about this for a second. Let's think about this for a second. So I'm trying to think. You've got 283.89 grams per mole. If we were to divide that out by 141.94 grams per mole, that would tell us how much of that we have. That would tell us how much of that we have. So let's go back to this over here. See how you have an X here and an X here? Let's come down here for a second. I'm going to factor that X out and put X times P O. Okay? I'm going to factor that X out. Just kind of like basic algebra stuff, right? And I know that you see a 2 and a 5 here. These are 2 different atoms, and in math class you go, okay, well, if I got 2 different variables, don't I need an X and a Y? Here the concept is the ratio is going to stay 2 phosphorus and 5 oxygen no matter what we've got. The question is this the simplest ratio, and if that increases, how much does it increase by? Well, the only way to know how much it increases by is to divide into it, which is why I put the larger value on top. Okay, so now if we divide this out right here, 283.89 divided by 141.94, you see that you get 2 with a whole lot of zeros, right? So that's 2.0000, finally 704, right? Well, what's the unit? Well, you got grams per mole on the top and you got grams per mole on the bottom. Those units are gone. This is one of those rare few times in math where no unit remains. The unit is gone. All right? The unit is gone. So we look at this and we go, this is essentially a value of 2. All right? So if we have 2 times what this was, 2 times this is P4, 2 times this, 2 times 2 is 4, and then 2 times that 5 would be O10. There's our molecular formula. So molecular formulas, remember, like your basic, like glucose, the empirical formula, the smallest ratio is CH2O, but glucose, the molecular formula is C6H12O6, right? So here, the same thing is true. Here, this right here is the empirical formula, the smallest ratio. This right here is the molecular formula. All right, and so if we, what's the formula for it? All right, so if we had to name this thing right here, right? So that would be what? Tetraphosphorus decoxide, right? It's pretty simple. Remember your molecular formula names. So that's it. So just recap on that a little bit here. This part right here, go back. Remember, you have a basic ratio, and it tells you in the problem this is your ratio. Using these numbers, 2 times the mass for each of these, that's where those numbers came from. We get this. And then we can assume grams per mole because we can assume we're dealing with X amount of stuff that's on a scale. So we can assume we're dealing with molar amounts, right? Either a portion of it or whatever the case may be. Now it tells us the molar mass right here of the substance. So knowing the molar mass of the substance, we see this number here, molar mass, we see that right here, that doesn't equal that. So we ask ourselves, this is how many more times more than this number? Well, the only way to do that is to divide in this smaller number into that. Okay? By doing that, that tells us what our multiplier is. We needed the multiplier. How many times do we take the simplest ratio and multiply it up to a higher value, to a higher ratio amount? If we have 1/2 of a pizza, or do we have, or do we say we have 4/8 of a pizza? We take those numbers and we multiply them up to a higher number, but the ratio is still the same. The same basic ratio is there. So that's what we did here. Okay? All right. I hope that helps. Go back, look over this, and use this to help you with your problem sets, and check in with me if you need some help. Take care.